Hello everyone. Today we are pleased to introduce you about our project CAMPS. The majority focus is about the measurement parts of the cardiac mapping system. These are our group members including Bantita, Nanchaya, Kanin, Pitimon, and Hilapat. First, let me introduce what is cardiac mapping system. Before the physician can do the ablation, the visualization is needed, and this is what we're trying to do. It can be done by providing the mapping catheter, ablation catheter, their circuits, the localizations all together. The cardiac mapping system is divided into two main parts, which are the mapping catheter for the sensing system and the ablation catheter for active system. So, let's get into detail. For mapping catheter, it consists of two main parts, which are the tip portion and the catheter shaft as indicated in the picture. At the tip portion, it is designed to have 4 splines with 4 electrodes each. The electrodes are in the ring shape with 1 mm in size and 3 mm spacing. Therefore, with this design, it becomes a directionless catheter. At the shaft, it is where the wires will be assembled and is designed to be 8.5 French in size. To track the position, an Aurora tracking system wire will be coated with polyimide and is inserted in a tube to reduce the friction. Lastly, the braided stainless steel is provided to maintain the structure of the catheter. And next will be about the circuit.
Okay, before going to our circuit diagram designing, let's start with some characteristics of intracardiac electrogram or EGM, which have the effect on our circuit designing for signal amplifying and filtering. The first thing out about the amplitude of the EGM. This parameter used to design the gain of our amplifier to be able to use the EGM as the input for another circuit. The amplitude of the ventricle EGM are about 5 to 30 mV and atrial EGM are about 1.5 to 6 mV. And the most important thing is the amplitude of the bipolar EGM, which observed to identify the heart condition by the doctor and used for our impedance and magnetic localized imaging. And the amplitude of the bipolar EGM is in the range of 0.315 to 0.593 mV. And the frequency bandwidth of the EGM are between 30 to 500 Hz. From these characteristics of the EGM, we have designed a circuit to process the EGM before using other systems. And since we use the bipolar EGM, so the system starts from the 2 electrodes, sense the electrical potential from the heart, and then each of them will get into their own high pass and low pass filter, which have the cutoff frequency at 30 Hz and 500 Hz respectively. And then the 2 signals will get into the instrumentation amplifier and analog to digital converter of ADS12998, and the gain of amplifier is at 24 times, and the ADC has 24 bits and 16 kilo sampling per second. And the signal will send to the microcontroller and forward to the display interface, the magnetic localized imaging system, and impedance localized imaging system.
Okay, moving to the ablation catheter. It is the key equipment in the ablation procedure. Next, ablation is a procedure that is used to treat an abnormal heartbeat by using a radio frequency, which is an electrical current, in order to create resonance in the target site. This method helps patients to restore their regular heartbeat. And as mentioned before, an ablation can't be performed without an ablation catheter. This picture demonstrates our ablation catheter design. For an external appearance, it can be seen that this catheter consists of a pair of ring electrodes and 1 ablation electrode at the tip. Also, there are 6 satellite ports since it is an irrigated ablation catheter. The size is designed to be about 8 French. Lastly, the catheter shaft is made from woven dacron with a usable length of 150 centimeters. And to be more in a detail of the ablation catheter component, there are about 7 components exist within the catheter as you can see on the slide. And we will go in a detail next slide. First one, we have 6 saline pores at the catheter tip with a diameter of 0.4 millimeters. The infused saline is sent from the saline port to the tip via flexible tube with a diameter of 0.7 millimeters. The saline flow rate is about 10 to 30 milliliters per minute. It used to cool catheter tip during the ablation. And next is a ring electrode. It is embedded at the tip with the size of 1 millimeter. It is used to record a bipolar EGM during the ablation. There is one more electrode located at the distal end, which is 4 millimeter tip electrode. This electrode receives radio frequency and deliver it to the ablation site. All the electrodes are made from platinum coated with iridium to prevent thrombosis. And pressure sensor is used to determine the contact between catheter tip and myocardium in order to initiate an ablation process. When the catheter touches the tissue, the pressure within the catheter is raised since the saline pores are blocked by the tissue. So this is detected by the pressure sensor. And next we have a thermocouple. It is used to measure the temperature of the catheter tip. It used to determine an adequate amount of radio frequency for ablation. And contact force also needed to tell the physician to know the precise contact force that needs to be applied during the ablation process. And lastly, we have magnetic sensor. It used to tell the location of the ablation catheter. In our project, we decided to use an aurora sensor. And next slide, it shows a cross-section view of the ablation catheter. As you can see, the outermost part has 2 pulvar tendons mounted 180 degrees to each other. This is used to control the movement of the catheter. And next slide, it shows the optimal parameter of the ablation process. Begin with the first one. Radio frequency should be at 500 kHz with a power of 30 to 50 watt. And temperature should be about 55 to 60 degrees Celsius. And lastly, contact force should be about 15 to 20 G. And next will be about the circuit.
Okay, for the Radiofrequency Generator circuit, it started from a several oscillator generate a signal at 500 kHz and then go to the non-overlapping clock to separate the signal from a stable oscillator to 2 signals with 180 degree phase shift and delay to prevent the rising and falling edge of the 2 signals doesn't overlap with each other. These 2 signals then used to control the cycle of the center tap power transformers that will step the power up to 30 to 50 watt. Then the signal from the power transformer will pass through 500 kHz low pass filters to filter and change the signal into sinusoidal wave and go to the ablation site to the ablation electrodes. The voltage and the current used to ablation then sent to the voltage and current transformer and then to the peak detector circuit and send those detected voltage and current to the microcontroller. The microcontroller also get the pressure and temperature signal that used to process the control voltage to control the power of the power transformer by feeding the voltage to the center tap of the power transformers.
So for a localization system, next, it is a system used to determine the position and location. In cardiac mapping, the main functions of localization are 3D anatomical mapping, catheter visualization, and voltage localization. Conventionally, a localization system only relies on electromagnetic tracking system, but nowadays the localization systems are adapting to a hybrid system by the fact that it yields a more accurate tracking. The hybrid localization consists of 2 main methods, which are magnetic and impedance. Next, begin with the magnetic localization. There are 2 main components, which are the magnetic transmitter that's placed under the patient and a magnetic sensor embedded at the tip of the catheter. Next. So let's get to know the basic of how magnetic localization works. It begins with the magnetic coils generating the magnetic field. The immediate field are represented as color hemisphere. Then the magnetic sensor will detect the strength of the magnetic field and convert into distance. Therefore, the magnetic field strength will be inversely proportional to the distance, as the core will have higher field strength while the edge has lower field strength. Next. For the design, there will be in total of 8 transmitter coils divided into 2 layers around the patient as shown in the picture. Half of the transmitter are in the upper layer and the rest are in the lower. Also, we employ the C-arm design as it's well suitable with our magnetic transmitter. And for the sensor, a 5-degree of freedom magnetic sensor is used as is capable of detecting 3 position and 2 rotation angles, and also it is small. Next. For the circuit of the transmitter, it consists of 8 individual circuits that will supply current to generate the magnetic field. Also, each transmitter will generate the field at a different frequency. This allows the position relative to each transmitter to be determined. Next, for the circuit of the sensor, it consists of an instrumentation amplifier since the output voltage from the sensor is in the level of microvolt in which amplification is needed. Then the amplified signal will send to the data acquisition and to the computer for image processing. And that's basically all about magnetic localization. Next is the impedance localization.
For the impedance-based localization, we use localization technology called Localiza that works when an electrical current is externally applied to the thorax. The voltage drop will occur across the internal organs, which is the heart. This can be done by sensing voltage change between the catheter and reference point as a electrode, which will be used to determine the electrode position. Next. In this system, 3 skin electrodes were used to send 3 small 1 mA current to the thorax in 3 orthogonal directions with slightly different frequency of around 30 kHz. This will recreate voltage gradient at vertical field strength on X, Y, and Z axis. The voltage will drop according to the bioimpedance from internal organs around. For example, as you can see in the picture on X-axis, if the internal impedance is 150 ohms and the heart is 10 ohms, the catheter can be measured in the range of 150 to 160 milliohms. So when the physician put the catheter around the heart, data will be collected to draw the heart image later. Next. As mentioned, we will generate current at 1 mA at 30 kHz using enhanced Howland current pump circuit. The circuit is shown here. And next. However, after passing through the body parts, respiratory and cardiac movement may cause cyclic variation. So several band filters should be applied to eliminate this variation, but this may result in slowing down the response of catheter position as well. Next. Here is the schematic design of our filter circuit. Next. The signal will pass through the filter bank from its frequency axis. The filters are from, for example, ECG, EMG, and EGM, and respiratory. These signals will be deleted later. The signal will send through ADC named ADS131E04 and sent through the signal processing. Next. For conversion to catheter position, we will use voltage drop divided by vertical field strength and using Pythagoras. The final calculation will be give the distance in centimeter to locate the catheter in signal processing. Next. Additional information such as safety standard, limitation, future improvement, and reference will be explained in the report. And that's all for our presentation. Thank you very much.